The planet we see in textbooks isn't the planet that's really out there. And the discoveries being made right now are forcing us to rewrite the rules. Let me show you what Neptune has been hiding. When Voyager 2 flew past Neptune in August 1989, it captured images that would define our understanding of this world for generations. That deep, vibrant blue sphere became iconic. Posters, documentaries, science textbooks all featured Neptune as this stunning sapphire jewel of the outer solar system, distinctly different from its neighbor Uranus. There's just one problem with that image. It's not real. Well, it's real, but it's been dramatically enhanced. The color you've seen your entire life was artificially deepened to make Neptune's cloud features more visible for scientific study. The actual color of Neptune? It's much closer to the pale cyan of Uranus than anyone realized. This revelation came in late 2023 when researchers finally normalized the color data properly across different imaging systems. For over 30 years, we've been looking at an exaggerated version of Neptune. And if scientists got something that fundamental wrong for that long, what else have we missed? The answer is almost everything. Start with what Neptune is supposedly made of. We've called it an ice giant for decades. The term suggests a world dominated by water ice, methane ice, ammonia ice, frozen materials that accumulated far from the sun, where temperatures plummet to unimaginable lows. Standard planetary models describe a relatively simple three-layer structure: a small rocky core, a thick icy mantle, and a hydrogen-helium atmosphere on top. In December 2025, scientists published research that demolished this comfortable picture. Using advanced hybrid modeling techniques, they discovered something shocking. Neptune might not be icy at all. The planet could just as easily be dominated by rock as by water-rich ices. The rock-to-water mass ratio might range anywhere from 0.20 to 1.78. Think about what that means. We've categorized Neptune as an ice giant, but it might actually be more rock than ice. The entire classification could be wrong. It's like calling something a lake when it's actually mostly mud. This uncertainty exists because we've never sent a probe into Neptune's interior. Everything we know comes from gravitational measurements and observations of the magnetic field, data that can support multiple completely different internal configurations. The gravitational field tells us how mass is distributed, but it can't tell us what that mass actually is. Rock and ice under extreme pressure can produce similar gravitational signatures while being fundamentally different materials. If Neptune is rock-dominated rather than ice-dominated, we need to rethink how it formed. Current models already struggle with Neptune's formation. They can't quite explain how it grew large enough, fast enough, to capture its atmosphere before the early solar system's gas dissipated. If the planet's composition is radically different from what we assumed, those models become even more problematic. The implications reach beyond Neptune itself. Neptune mass planets are among the most common types of exoplanets we've discovered orbiting other stars. Understanding how our Neptune formed is critical to understanding planetary systems throughout the galaxy. If we've been wrong about our own ice giant, we might be wrong about thousands of distant worlds too. But Neptune's interior holds secrets stranger than just its composition. Deep within the planet, under pressures that would crush any material we know, something extraordinary happens. Methane molecules get squeezed so intensely that they break apart. Carbon atoms separate from hydrogen, and then those carbon atoms do what carbon does under extreme pressure. they crystallize into diamonds. This isn't speculation anymore. Scientists have recreated the process in laboratories. They subjected plastics, long chains of carbon and hydrogen, similar to what exists inside Neptune, to conditions mimicking the planet's interior. Nearly every carbon atom in the samples transformed into nanodiamonds, just a few nanometers wide. On Neptune, those diamonds would grow much larger. We're talking about diamonds millions of carats in weight. Some might be the size of buildings. These massive gemstones would be denser than the surrounding material, so they'd slowly sink deeper into the planet's interior, raining downward through layers of supersonic ice, a bizarre state of matter where oxygen atoms form a rigid crystalline structure while hydrogen ions flow through it like a liquid. Over thousands of years, this diamond rain might accumulate into a thick layer surrounding Neptune's core. The planet's interior could contain more diamond material than exists in Earth's entire crust. Mountains of diamonds, slowly precipitating through an ocean of exotic ice, all hidden beneath cloud tops, so cold they'd freeze you solid in seconds. This diamond rain serves a purpose beyond being spectacularly strange. When diamonds sink, they transport heat from the interior upward through convection. They also carry carbon deeper into the planet, potentially driving movements in those conductive ice layers. These movements might help generate Neptune's magnetic field, which brings us to another mystery entirely. Neptune's magnetic field doesn't make sense. On Earth, our magnetic field emerges from convection in the liquid iron outer core. The field aligns roughly with our rotation axis, with magnetic north relatively close to geographic north. Neptune's field does nothing of the sort. The field center is displaced by about 0.55 planetary radii, meaning the magnetic field center sits closer to Neptune's cloud tops than to the planet's actual center in some regions. The field is also tilted 46.9 degrees relative to Neptune's rotation axis. This creates one of the most bizarre magnetic configurations in the solar system. Here's what that means in practice. Neptune's auroras don't occur at the poles like Earth's northern and southern lights. Instead, they appear at mid-latitudes, roughly where South America would be if you mapped Earth's geography onto Neptune. The magnetic field wobbles dramatically as the planet rotates, creating a constantly shifting pattern that would seem utterly alien to anyone familiar with Earth's relatively stable magnetic environment. Scientists struggled to explain this configuration for years. Standard dynamo models, the theories describing how planetary magnetic fields generate, couldn't produce Neptune's lopsided, tilted field. The breakthrough came when researchers proposed that Neptune's magnetic field doesn't originate in a large convecting core like Earth's. Instead, it generates in thin shells of conducting material in the upper mantle. This model works, but it requires Neptune's interior to have a layered structure far more complex than the simple three-layer model we started with. Computer simulations suggest that under the extreme temperatures and pressures inside Neptune, water, methane, and ammonia naturally separate into distinct layers. It's like oil and water. They simply won't mix under these conditions. Hydrogen gets squeezed out of the methane and ammonia that dominate the deep interior, creating sharp boundaries between different material zones. These immiscible layers could explain both the strange magnetic field and why Neptune's field differs so dramatically from Earth's, Jupiter's, and Saturn's. It's an elegant solution to a decades-old puzzle, but it also means Neptune's interior is far more sophisticated and structured than anyone imagined. Supporting this complex internal structure is an exotic molecule that cannot form on Earth. aquadium. Under the extreme pressures inside Neptune, hydrogen and oxygen can bond in configurations impossible under normal conditions. These exotic molecules might fill those thin conducting shells, generating the magnetic field through mechanisms we're only beginning to understand. The magnetic field mystery connects to another unexpected discovery. In March 2025, the James Webb Space Telescope finally captured clear images of Neptune's auroras. Astronomers had been trying to confirm auroral activity since Voyager 2 flew past in 1989. But those early observations only showed hints. JWST settled the question definitively, but the auroral observations revealed something troubling. Neptune's atmosphere has cooled dramatically in recent decades. Global temperatures in the stratosphere dropped by roughly 8 degrees Celsius between 2003 and 2018. This was completely unexpected. Neptune experiences seasons like Earth does, but each season lasts over 40 Earth years because Neptune takes 165 years to orbit the Sun. Scientists expected temperatures to be slowly rising during Neptune's early southern summer, not falling. Then things got even stranger. Between 2018 and 2020, Neptune's south polar region warmed by roughly 11 degrees Celsius, completely reversing the global cooling trend. Such rapid polar warming had never been observed on Neptune before. The cause remains unknown. Several theories attempt to explain these temperature swings. Changes in atmospheric chemistry might alter how efficiently the atmosphere radiates heat into space. Random weather variability could create temporary hot or cold periods. Neptune might somehow respond to the Sun's 11-year activity cycle, even though the planet receives only about 0.1% of the sunlight Earth gets. That last possibility is particularly intriguing because it shouldn't work. Neptune is so distant that solar variations should barely register. Yet the atmosphere seems surprisingly responsive to solar changes. It's as if Neptune has an amplification mechanism we don't understand, making the planet's atmosphere far more sensitive to external influences than physics suggests it should be. These temperature mysteries connect to Neptune's most paradoxical feature, its weather. The planet experiences the strongest sustained winds in the solar system, reaching speeds up to 2,100 kilometers per hour. That's 9 times stronger than the strongest winds on Earth. These supersonic gales tear across cloud tops where temperatures hover around negative 218 degrees Celsius, one of the coldest places in the solar system. This shouldn't be possible. Weather requires energy. On Earth, our weather systems are powered by solar heating. Warm air rises, cold air sinks, and the temperature differences drive circulation patterns that create wind. Neptune receives so little solar energy that it should be meteorologically dead, or at least sluggish. Instead, Neptune's atmosphere is violently active. Storm systems emerge and evolve within hours. Giant vortices larger than Earth circle the planet in 16 to 18 hours. The only explanation that makes sense is that Neptune's weather is powered primarily by internal heat rather than sunlight. And Neptune does generate substantial internal heat. The planet radiates about 3 times more energy than it receives from the Sun. Temperatures at Neptune's center reach approximately 5,400 Kelvin, nearly as hot as the surface of the Sun. This internal heat flows outward, driving atmospheric circulation and powering those impossible winds. But this creates yet another puzzle. Where does that internal heat come from? Neptune formed billions of years ago. It should have radiated away most of its primordial heat by now, leaving it as cold internally as it is externally. Something must be generating heat inside the planet, or some mechanism is preventing that heat from escaping as quickly as it should. The diamond rain might be part of the answer. As diamonds crystallize and sink, they release gravitational potential energy that converts to heat. The separation of those immiscible interior layers could also generate heat through a process called differentiation. Or perhaps heat is trapped by those layered structures, insulated from escaping into space by the complex internal architecture. Whatever the mechanism, that internal heat makes Neptune far more active than it has any right to be. And that activity manifests in ways that continue to surprise us. The storms themselves behave unlike anything seen elsewhere in the solar system. Neptune's most famous storm, the Great Dark Spot discovered by Voyager 2 in 1989, had completely vanished by the time Hubble observed Neptune just 5 years later. These massive anticyclonic vortices appear, rage across the planet for a few years, then disappear without a trace. In 2018, Hubble spotted a new dark vortex in Neptune's northern hemisphere. Observations in 2019 showed it drifting southward toward the equator, where such storms are expected to dissipate. Scientists prepared to watch the storm's death. Then in August 2020, something unprecedented happened. The storm reversed course. It doubled back northward, defying every prediction about how Neptunian storms should behave. This was the first time scientists had observed a storm on any planet abruptly change direction like this. Then Hubble spotted something even stranger. A smaller dark spot appeared briefly near the larger storm, possibly a piece that broke off before disappearing entirely. Computer simulations had predicted that Neptunian storms might break apart and spawn smaller vortices, but no one had ever observed it happening. The fact that this process occurred during one of the few times we were watching closely suggests it might be common. We've just never had the capability to monitor Neptune continuously enough to catch these events. The storms themselves form through a process we're only beginning to understand. Cloud activity increases in a region 2 to 3 years before a dark spot becomes visible. Something happens deep in the atmosphere, triggering enhanced convection that eventually manifests as a massive visible vortex. What triggers that initial activity remains unclear. These mysteries aren't confined to Neptune's atmosphere. The planet's ring system contains features that shouldn't exist according to everything we know about orbital mechanics. Neptune has 5 distinct ring arcs, concentrated segments within the Adam's ring, named Fraternité, Égalité 1 and 2, Liberté, and Courage. These arcs occupy narrow ranges of orbital longitude and have remained remarkably stable since their discovery in 1984. This stability is impossible. Differential orbital motion should cause these arcs to spread out and dissipate within just a few months. Particles closer to Neptune orbit faster than those farther out, so any concentrated arc should smear into a uniform ring almost immediately. Yet Neptune's arcs have persisted for over 40 years. The leading theory suggests gravitational resonance with Neptune's moon Galatea somehow maintains the arcs, but the mechanism remains unclear. Recent observations have made the mystery deeper. The arcs Courage and Liberté have faded away, while Fraternité and Égalité remain stable. Why would some arcs disappear while others persist? Neptune's rings themselves are made of extremely dark material, likely organic compounds processed by radiation over billions of years. The proportion of dust in these rings is unusually high, between 20 and 70%. Most planetary rings are dominated by larger particles with only trace amounts of dust. Neptune's dust-rich rings suggest either a unique formation process or ongoing destruction of larger particles into smaller fragments. Every observation of Neptune reveals more questions than answers. The planet that seemed straightforward, a cold, distant ice giant, turns out to be one of the most complex and mysterious worlds in our solar system. From its possibly rocky interior to its diamond rain, from its bizarre magnetic field to its impossible weather, from its reversing storms to its paradoxical ring arcs, Neptune defies explanation at every level, and we've barely scratched the surface. Neptune's largest moon, Triton, presents its own collection of impossibilities, a world that shouldn't be where it is, shouldn't be geologically active, yet somehow manages both. The mysteries compound with every measurement, every observation, every attempt to understand this distant world. But here's what makes all of this truly fascinating. Neptune isn't just weird for the sake of being weird. Every strange feature, every unexpected discovery points toward fundamental gaps in our understanding of how planets work. The answers to Neptune's mysteries will reshape our comprehension of planetary science itself. And those answers are starting to emerge in ways no one anticipated. Triton shouldn't exist where it does. Neptune's largest moon orbits backward, retrograde motion completely opposite to Neptune's rotation. Every other major moon in the solar system orbits in the same direction as its planet spins. Triton alone breaks this rule. The implications are staggering. Retrograde orbits don't form naturally during planetary formation. The material that coalesces into moons carries the angular momentum of the original protoplanetary disk, creating orbits that match the planet's rotation. Always, without exception, except Triton. The only explanation that makes sense is capture. Triton wasn't born around Neptune. It came from somewhere else, likely the Kuiper Belt, that distant realm of icy objects beyond Neptune's orbit. Somehow, billions of years ago, Triton wandered too close to Neptune. Gravitational interactions slowed it down just enough to trap it in orbit. This capture event would have been catastrophic. Any moons already orbiting Neptune would have been scattered or destroyed by Triton's arrival. The gravitational chaos would have reshaped the entire system. We're looking at the aftermath of a cosmic collision that fundamentally altered Neptune's satellite architecture. But here's what makes Triton truly bizarre. It's geologically active. Voyager 2 discovered this in 1989, spotting active geysers erupting from Triton's surface. Nitrogen geysers, shooting material 8 kilometers into the thin atmosphere before winds carried it hundreds of kilometers downrange. Triton's surface temperature measures negative 391 degrees Fahrenheit. It's one of the coldest objects we've ever measured in the solar system. At those temperatures, nitrogen freezes solid. Yet somehow, something generates enough heat to create active geology. The leading theory involves tidal heating. As Triton orbits Neptune, gravitational forces flex and squeeze the moon's interior, generating friction and heat. But the calculations don't quite work. Triton's orbit is nearly circular now, which should minimize tidal heating. The amount of geological activity we observe seems impossible given the orbital configuration, unless Triton's interior contains something unexpected, some heat source we haven't accounted for. Or perhaps the tidal heating was more intense in the past, and we're seeing the delayed effects. Thermal energy slowly working its way to the surface over millions of years. Triton's geology itself defies easy explanation. The surface displays cantaloupe terrain, strange dimpled landscapes unlike anything else in the solar system. These features might represent cryovolcanic activity, where water-ammonia mixtures erupt instead of molten rock. But the exact formation mechanism remains unclear. The Moon's future is equally fascinating and tragic. Triton's retrograde orbit creates tidal interactions that gradually drain orbital energy. The Moon is slowly spiraling inward toward Neptune. In 3.6 billion years, Triton will cross Neptune's Roche limit, the distance at which tidal forces overcome the Moon's self-gravity. When that happens, Triton will either crash into Neptune's atmosphere or be torn apart by tidal forces. If it breaks apart, the debris will form a new ring system around Neptune, potentially rivaling or exceeding Saturn's magnificent rings. Future astronomers, billions of years from now, will observe a Neptune surrounded by spectacular rings made from the shattered remains of its largest moon. For now, Triton remains one of the most intriguing objects in the outer solar system, a captured Kuiper Belt object displaying active geology despite temperatures that should freeze all activity solid, a moon orbiting backward, slowly falling toward inevitable destruction. But Triton isn't Neptune's only moon. The system contains 14 known satellites, most of them small, irregular bodies likely captured from the Kuiper Belt alongside Triton. These outer irregular moons orbit at extreme distances, some taking more than 25 years to complete a single orbit. One of these moons, Nereid, has the most eccentric orbit of any large moon in the solar system. Its distance from Neptune varies by a factor of 7 during each orbit, from 1.4 million kilometers at closest approach to 9.7 million kilometers at its farthest point. This extreme elliptical orbit suggests Nereid might have been perturbed by Triton's capture event, flung into its current strange trajectory by the gravitational chaos. The inner regular moons, Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus, orbit close to Neptune within the ring system. These moons are small, dark, and irregularly shaped. They're likely remnants of the original satellite system that survived Triton's arrival. Or perhaps they formed from debris after the capture event destroyed the original moons. Proteus deserves special mention. It's the second largest Neptunian moon after Triton, yet it wasn't discovered until Voyager 2's flyby, despite being larger than Nereid, which had been known since 1949. The reason? Proteus orbits so close to Neptune and reflects so little light that it remained invisible to Earth-based telescopes until spacecraft arrived. Proteus itself shouldn't exist in its current form. At 420 kilometers in diameter, it's right at the threshold where self-gravity should pull an object into a spherical shape. Yet Proteus is distinctly non-spherical, covered in craters and angular features. It appears to be as large as a body can get while remaining irregularly shaped. Any bigger, and it would collapse into a sphere. The regular moons interact with Neptune's ring system in complex ways. Galatea appears to shepherd the ring arcs, using gravitational resonances to maintain their stability. But the exact mechanism remains unclear, especially given the selective fading of some arcs while others persist. These moons and rings tell a story of violence and chaos in Neptune's past. The current configuration didn't emerge from orderly planetary formation. It's the result of capture events, gravitational disruptions, and ongoing orbital evolution that continues to reshape the system today. What triggered Triton's capture? How did it lose enough energy to become bound to Neptune? These questions have no definitive answers. One possibility involves a binary system, two Kuiper Belt objects orbiting each other. If this binary wandered close to Neptune, tidal forces could have separated the pair, with one object escaping, while the other lost enough energy to be captured. Another scenario involves a three-body interaction with another planet. Perhaps Triton encountered Neptune during an era when the outer solar system was still dynamically active, with planets migrating and crossing orbits. A close encounter at just the right moment could have resulted in capture. Regardless of the mechanism, the capture must have been spectacular. The newly captured Triton would have been in a highly elliptical orbit, swinging far from Neptune before plunging back close to the planet. Tidal forces would have been extreme during these close passages, generating immense heat in Triton's interior. The moon might have been partially molten during this phase, thoroughly resurfacing and erasing any record of its earlier history. Over millions of years, tidal interactions gradually circularized Triton's orbit, while simultaneously causing it to spiral inward. The orbital energy dissipated as heat, both in Triton's interior and in Neptune's atmosphere. This process continues today, though at a much slower rate, given the now circular orbit. The tidal heating history explains Triton's relatively young surface. Voyager 2 found few impact craters on Triton compared to other icy moons, suggesting the surface has been resurfaced within the last few million years. Geologically recent, the nitrogen geysers might be the last gasps of a once much more vigorous geological activity, powered by tidal heating. Triton's atmosphere adds another layer of mystery. Despite the extreme cold, the moon maintains a thin nitrogen atmosphere with trace amounts of methane. Atmospheric pressure is only 14 microbars, 70,000 times thinner than Earth's atmosphere. Yet this tenuous envelope creates weather, clouds, and seasonal changes. As Triton orbits Neptune, different hemispheres experience sunlight and darkness over the course of Neptune's 165-year orbital period. This creates extreme seasonal effects. Nitrogen ice sublimates in sunlight and condenses in darkness, causing the atmospheric pressure to vary dramatically over decades. We've observed Triton during only a tiny fraction of its seasonal cycle, leaving most of its atmospheric behavior unknown. The moon's surface composition includes nitrogen ice, methane ice, carbon monoxide ice, and water ice, along with complex organic compounds that give some regions a pinkish color. This chemistry responds to solar radiation and seasonal temperature changes in ways we're only beginning to understand. Some scientists have proposed that Triton's subsurface might harbor a liquid water ocean beneath the icy crust. Tidal heating, combined with antifreeze compounds like ammonia, could maintain liquid water even at Triton's extreme distance from the Sun. If such an ocean exists, it would make Triton one of the most intriguing astrobiology targets in the solar system, a potential habitat for life in one of the coldest, darkest corners of our planetary family. Testing this hypothesis requires a dedicated mission to Triton, something that hasn't happened yet despite numerous proposals. The moon's retrograde orbit makes it challenging to reach. Spacecraft approaching Neptune must match this backward motion, requiring more fuel and more complex trajectory planning than missions to prograde orbiting moons. Yet the scientific payoff would be enormous. Understanding Triton means understanding Kuiper Belt objects, since Triton is essentially a captured Kuiper Belt dwarf planet. It's our closest large example of that distant population, preserved in orbit around Neptune, where we can study it in detail. Triton might also tell us about Neptune's formation and early evolution, The gravitational interactions during capture would have revealed information about Neptune's mass distribution and internal structure. Modeling the capture event requires understanding Neptune's properties at that time, which in turn constrains how the planet formed and evolved. The Moon's geological activity connects to Neptune's own mysteries. If tidal heating can drive geology on Triton, despite the extreme cold, perhaps similar processes operate within Neptune itself, contributing to the planet's anomalous heat output. The relationship between Moon and planet might be more complex than simple gravitational interaction. Every aspect of Triton challenges our expectations. A moon orbiting backward, active geology at temperatures that should freeze everything solid, a tenuous atmosphere that somehow persists despite constant loss to space, a captured body that survived the violence of its own capture to become Neptune's dominant satellite. The story of Triton is ultimately the story of Neptune itself, a system that refuses to behave as predicted, that generates mysteries faster than we can solve them, that reveals the universe to be stranger and more complex than our theories suggest. Understanding one requires understanding the other, and both remain tantalizingly just beyond our complete comprehension. The mysteries don't end with Triton. Neptune's ring system presents puzzles that fundamentally challenge our understanding of orbital dynamics. Most planetary rings form complete circles: Saturn's rings, Uranus's rings, Jupiter's faint gossamer rings. They all follow a basic principle: material orbiting a planet spreads out evenly over time, creating uniform structures governed by simple gravitational mechanics. Neptune's rings refuse to cooperate. The Adam's ring, Neptune's outermost ring, contains 5 distinct arcs with peculiar French revolutionary names: Fraternité, Égalité 1 and 2, Liberté, and Courage. These arcs occupy only specific sections of the ring's orbit, concentrated in narrow ranges of longitude, while the rest of the ring remains nearly empty. This shouldn't be possible. Differential orbital motion, the fact that inner material orbits faster than outer material, should smear these arcs into complete rings within months. Every calculation says they should have dispersed decades ago, yet they persist, stable and distinct, having changed only slightly since their initial detection in 1980. The explanation involves Galatea, a small inner moon that acts as a shepherd, using resonant gravitational interactions to confine the arc material. The mathematics works, technically, but barely. The system operates on a knife edge between stability and chaos. Remove Galatea, and the arcs would vanish. Alter the resonance slightly, and the structure collapses. Recent observations have complicated the picture further. The leading arcs, Courage and Liberté, have faded significantly or disappeared entirely. The trailing arcs, Fraternité and Égalité, remain persistent and stable. This selective disappearance wasn't predicted by any model. Why would some arcs vanish while others endure under identical physical conditions? The ring material itself adds another layer of mystery. Neptune's rings are composed of extremely dark material, likely organic compounds that have been processed by radiation over millions of years. The proportion of dust ranges between 20 and 70%, unusually high compared to Saturn's ice-dominated rings. This dusty composition makes the rings incredibly difficult to observe from Earth, requiring long exposures and careful image processing to detect at all. The optical depth of the rings remains low, meaning they contain relatively little material despite their vast extent. Where did this material come from? Was it captured from passing comets, debris from destroyed moons, material left over from Neptune's formation? Each possibility has problems, Captured material should have different compositions across the ring system. Destroyed moons should have created more debris. Primordial material should have been swept away or accreted long ago. The ring's darkness suggests something else entirely. Perhaps a chemical evolution we don't yet understand, where radiation and charged particles gradually transform simple ices into complex organic compounds. This process might be ongoing, continuously darkening the ring material over astronomical timescales. Voyager 2's brief encounter in 1989 captured our only close-up images of Neptune's rings. Those images revealed structure and detail impossible to see from Earth. But they also raise questions that remain unanswered 35 years later. The spacecraft's trajectory allowed only a snapshot, one moment in time for a dynamic system that evolves over decades and centuries. What we need is time, continuous monitoring, observations across multiple Neptunian seasons to watch how the rings change, how the arcs evolve, whether new structures form or existing ones disappear. From Earth, even with our most powerful telescopes, Neptune's rings appear as faint smudges, requiring hours of integration time to detect. The discovery of Neptune itself stands as one of astronomy's greatest intellectual achievements. Unlike every other planet, Neptune was found through mathematics before it was seen through telescopes. In the early 1800s, astronomers noticed something odd about Uranus. The planet wasn't where it should be. Its orbit deviated slightly from predictions based on Newtonian mechanics and the gravitational influence of the known planets. These deviations were small but persistent, and they suggested the presence of an eighth planet beyond Uranus, tugging on it with invisible gravitational force. Alexis Bouvard documented these irregularities, but died before solving the puzzle. Two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently calculated where this hypothetical planet should be located based solely on Uranus's orbital perturbations. Le Verrier's calculations proved more influential. He sent his predictions to Johann Gottfried Galle at the Berlin Observatory, and on September 23, 1846, Galle pointed his telescope to the predicted location. Neptune appeared within 1 degree of Le Verrier's calculated position. This represented a stunning validation of Newtonian mechanics and mathematical astronomy. A planet had been discovered not through systematic sky surveys or accidental observation, but through pure theoretical calculation. The universe, it seemed, could be understood through equations. Gravity operated predictably across billions of kilometers. Mathematics revealed reality. Yet Neptune itself immediately began complicating this elegant picture. The planet's mass turned out to be different than predicted. About 17 Earth masses rather than the 30+ predicted by Le Verrier's calculations. The mathematical prediction had worked despite being based on partially incorrect assumptions. Lucky coincidence, or something deeper? Even today, Neptune's discovery raises philosophical questions about scientific prediction and the nature of scientific success. The calculations were wrong in detail, but right in principle. Does this represent the power of mathematical modeling or its limitations? Neptune's atmospheric behavior continues generating surprises. Between 2003 and 2018, collective datasets showed a decline in the planet's thermal brightness, indicating that globally average stratospheric temperatures dropped by roughly 8 degrees Celsius. This was completely unexpected. Neptune experiences seasons like Earth, but each season lasts over 40 Earth years due to the planet's 165-year orbital period. Scientists expected temperatures to be slowly growing warmer during early southern summer, following the increasing solar heating as that hemisphere tilted toward the sun. Instead, temperatures fell dramatically. Then, in 2018, something even stranger happened. Observations from Gemini North and the Subaru telescope revealed that Neptune's polar stratosphere warmed by roughly 11 degrees Celsius between 2018 and 2020, completely reversing the previous cooling trend. Such rapid polar warming had never been observed on Neptune before. The cause remains unknown. Several theories attempt to explain these temperature swings, changes in atmospheric chemistry that alter cooling efficiency, random weather pattern variability, or responses to the 11-year solar activity cycle. The solar connection is particularly intriguing because Neptune receives only about 0.1% of the sunlight that Earth receives, yet its atmosphere appears surprisingly responsive to solar variations. How can a planet so distant from the Sun, receiving such minimal solar energy, show measurable atmospheric responses to solar cycles? What mechanism could amplify such weak forcing into the dramatic temperature changes we've observed? The thermosphere presents an even greater mystery. For reasons that remain obscure, this upper atmospheric layer maintains temperatures around 750 Kelvin, hot enough to melt lead. Neptune is too far from the Sun for ultraviolet radiation to generate this heat. Something else must be warming the thermosphere to such extreme temperatures. Candidates include atmospheric interaction with ions in Neptune's magnetic field, creating friction and heating similar to auroral processes on Earth. Gravity waves from the interior might dissipate in the upper atmosphere, converting mechanical energy into heat. Chemical reactions involving unexpected compounds could release energy. None of these explanations fully accounts for the observed temperatures. The planet's internal heat generation compounds the puzzle. Neptune emits about 3 times as much energy as it receives from the Sun. This excess energy must come from the interior, but the mechanism remains uncertain. Core cooling, gravitational contraction, chemical reactions in the deep interior, radioactive decay, each process contributes something, but the exact proportions and their interactions remain unclear. Temperatures at Neptune's center reach approximately 5,400 Kelvin, hot enough to glow if you could somehow see through the overlying layers. This internal heat drives the planet's dynamic weather, powering winds that reach 2,100 kilometers per hour, the strongest sustained winds of any planet in the solar system. How can a planet so cold at its cloud tops maintain such powerful atmospheric circulation? How does internal heat propagate through thousands of kilometers of dense material to reach the atmosphere and drive such violent weather? The energy transport mechanisms remain poorly understood. In March 2025, the James Webb Space Telescope finally captured Neptune's aurorae in detail, ending decades of speculation since Voyager 2 caught only tantalizing hints. The observations revealed something unexpected. The Neptunian atmosphere has cooled by hundreds of degrees in recent decades, making the aurora fainter than anticipated. But it's the location of these aurorae that truly defies expectation. Neptune's magnetic field is tilted 47 degrees away from its rotation axis, which means aurorae occur roughly over regions equivalent to where South America would be on Earth, rather than at the poles. Unlike Earth's polar light shows, Neptune's aurorae appear at mid-latitudes, creating an alien spectacle that hypothetical observers would witness without traveling to extreme latitudes. The magnetic field itself remains one of Neptune's most profound mysteries. The field center is displaced by about 0.55 planetary radii from Neptune's geometric center and tilted 46.9 degrees relative to the rotational axis. This dramatic offset means the magnetic field center is actually closer to Neptune's cloud tops than to its planetary core in some regions. Both Uranus and Neptune share this bizarre magnetic configuration. Highly tilted fields significantly offset from the planet's centers. This similarity suggests a common mechanism, something fundamental about ice giant interiors that generates magnetic fields differently than terrestrial planets or gas giants. Recent research points toward an exotic molecule called aquadium, a substance that cannot be formed under Earth conditions. Computer simulations show that under the extreme temperatures and pressures inside Neptune, water, methane, and ammonia would naturally separate into immiscible layers like oil and water. Hydrogen would be squeezed out of the methane and ammonia that comprise much of the deep interior, creating distinct chemical zones. These layered, stratified regions could generate magnetic fields in thin shells of conducting material in the upper mantle, rather than through coherent convection in a large liquid core like Earth's dynamo. This would create a complex, multipolar field that wobbles dramatically as the planet rotates. Exactly what we observe. This oil and water-like interior structure could explain many of Neptune's peculiar properties: the magnetic field, the heat flow, the atmospheric dynamics, perhaps even the planet's surprising responsiveness to solar variations despite its extreme distance from the Sun. But it also raises new questions. How stable are these immiscible layers? Do they mix over geological timescales? Could convective processes occasionally breach the boundaries between layers, creating episodic changes in Neptune's magnetic field or heat output? We've observed Neptune for less than 2 centuries, a blink compared to the billions of years of its existence. Neptune's interior composition itself has recently been called into question by groundbreaking research from December 2025. Scientists now propose that Neptune may not be the icy world long imagined. New hybrid modeling reveals the planet could just as easily be dominated by rock as by water-rich ices, with rock-to-water mass ratios potentially ranging between 0.20 and 1.78. This discovery fundamentally challenges Neptune's classification as an ice giant. If the planet is more rock-dominated than ice-dominated, it would require completely rethinking how these distant worlds formed and evolved over billions of years. The uncertainty stems from never having sent a probe deep into Neptune's interior. Current models based on gravitational data and magnetic field observations can support multiple internal configurations: ice-dominated, rock-dominated, or something in between. Every measurement we have of Neptune is consistent with radically different interior structures. We've been building theories on ambiguous data, assuming ice giant composition because it seemed reasonable, not because we had definitive proof. The implications are staggering. Everything we thought we knew about Neptune's formation might need revision. If Neptune contains more rock than ice, it couldn't have formed where it currently resides. The outer solar system 4 billion years ago simply didn't contain enough rocky material at Neptune's distance to build a rock-dominated planet. This would mean Neptune formed much closer to the Sun, perhaps where Mars orbits today, and migrated outward through gravitational interactions with other planets. The nice model of solar system evolution already suggests the giant planets migrated from their birth positions, but a rock-dominated Neptune would require far more dramatic migration than previously imagined. But Neptune's mysteries extend far beyond its hidden interior. The planet's atmosphere presents puzzles that have confounded scientists for decades. Between 2003 and 2018, collective datasets showed Neptune's thermal brightness declining steadily, indicating globally average stratospheric temperatures dropped by roughly 8 degrees Celsius. This was completely unexpected. Neptune was entering early southern summer during this period. Scientists anticipated temperatures would slowly increase as that hemisphere received more sunlight, not plummet. Then something even stranger happened. Observations from Gemini North in 2019 and the Subaru telescope in 2020 revealed Neptune's south pole had warmed by roughly 11 degrees Celsius between 2018 and 2020. In just 2 years, the polar region reversed the previous 15-year cooling trend. Such rapid polar warming had never been observed on Neptune before. The cause remains unknown. Neptune experiences seasons like Earth, but each season lasts over 40 Earth years due to its 165-year orbital period. These aren't subtle seasonal variations. They're dramatic temperature swings across a world that receives only 0.1% of the sunlight Earth receives. How can Neptune's atmosphere respond so dramatically to such minimal solar input? Scientists have proposed multiple theories. Changes in atmospheric chemistry altering how effectively the atmosphere radiates heat, random weather pattern variability, or responses to the 11-year solar activity cycle, but none fully explain the observations. The solar connection is particularly perplexing. Neptune orbits 30 times farther from the Sun than Earth. At that distance, solar radiation should be negligible, yet Neptune's stratosphere appears surprisingly responsive to solar variations. During solar maximum, when the Sun's output increases slightly, Neptune's upper atmosphere brightens. During solar minimum, it dims. The mechanism connecting such weak solar variations to atmospheric changes on this distant world remains one of planetary science's most intriguing puzzles. Neptune's internal heat adds another dimension to this mystery. The planet emits about 3 times as much energy as it receives from the Sun. This isn't reflected sunlight. It's heat flowing outward from Neptune's interior. Temperatures at Neptune's core reach approximately 5,400 Kelvin, hotter than the surface of the Sun. This internal furnace drives the planet's weather systems, powering storms and winds, despite the minimal solar energy available. And what weather it creates. Neptune possesses the strongest sustained winds in the solar system, speeds reaching 2,100 kilometers per hour, nearly twice the speed of sound on Earth. These supersonic winds roar through an atmosphere where cloud-top temperatures approach 55 Kelvin, making Neptune's outer atmosphere one of the coldest places in the solar system. The paradox is profound. The coldest planetary atmosphere generating the fastest winds. The source of this atmospheric energy remains debated. Neptune's internal heat certainly contributes, but converting that heat into organized atmospheric motion at such extreme speeds requires mechanisms we don't fully understand. The planet's rapid rotation, a day lasts only 16 hours, creates powerful Coriolis forces. The thin atmospheric pressure allows winds to accelerate without the friction that limits terrestrial wind speeds. But these factors alone don't explain Neptune's extreme weather. Then there are the storms themselves. Dark spots appear and disappear on Neptune with bewildering unpredictability. These massive anticyclonic vortices, similar to Jupiter's Great Red Spot, behave unlike storms anywhere else. Astronomers using the Hubble Space Telescope watched one dark vortex discovered in 2018 begin drifting southward toward Neptune's equator, where such storms typically dissipate. But in August 2020, the vortex suddenly reversed course, doubling back northward. This represented the first time scientists had observed a Neptunian storm change direction. Computer simulations predicted such reversals were possible, but nobody had witnessed one. Then Hubble spotted another smaller dark spot in January that temporarily appeared near the larger vortex. Scientists speculated it might be a piece that broke off, drifted away, and disappeared, a process predicted by models but never observed. Dark spots on Neptune differ dramatically from Jupiter's long-lived storms. The Great Dark Spot discovered by Voyager 2 in 1989 had completely vanished by the time Hubble observed Neptune in 1994. These storms typically last only a few years. Their origins are preceded by increased cloud activity in a given region 2 to 3 years before the dark spot becomes visible. Their disappearance has been linked to companion clouds reaching the storm's center and blocking the blue wavelengths used to track the vortex. What drives these ephemeral storms? Why do they form, migrate, reverse course, and vanish so quickly compared to Jupiter's centuries-old storms? The answer probably involves Neptune's internal heat flow, its rapid rotation, and complex interactions between atmospheric layers. But the details remain frustratingly elusive. Neptune's thermosphere presents yet another atmospheric enigma. This outermost atmospheric layer maintains temperatures around 750 Kelvin, far hotter than would be expected for a world so distant from the Sun. Neptune is too far for ultraviolet radiation to generate such heat. One candidate heating mechanism involves atmospheric interactions with ions in Neptune's bizarre magnetic field. Another suggests gravity waves from the interior dissipate in the thermosphere, converting mechanical energy to heat. But neither explanation is proven. The planet's rings add another layer of mystery. Neptune possesses 5 main rings: Gale, Leverrier, Lassell, Arago, and Adams, along with several fainter dusty sheets. The Adams ring contains 5 distinct arcs named Fraternité, Égalité, 1 and 2, Liberté, and Courage. These arcs occupy narrow ranges of orbital longitude and have remained remarkably stable since their initial detection in 1980. They shouldn't exist. According to orbital mechanics, differential Keplerian motion should cause these arcs to spread out and dissipate within months. Each particle in the arc orbits at a slightly different speed based on its distance from Neptune. Over time, faster-moving inner particles should overtake slower outer particles, causing the arc to smear into a uniform ring. Yet these arcs have persisted for decades. Their stability probably relates to resonant interactions with Galatea, Neptune's inner shepherd moon. Galatea's gravity creates regions where particles can accumulate and remain confined, but the mathematics don't perfectly predict the observed arc positions and stability. Recent observations add another puzzle. The leading arcs, Courage and Liberté, have faded away, while the trailing arcs, Fraternité and Égalité, remain persistent and stable. Why would some arcs disappear while others endure? Neptune's rings consist of extremely dark material, likely organic compounds processed by radiation, similar to material in Uranus's rings. The proportion of dust in Neptune's rings ranges between 20 and 70%, unusually high compared to Saturn's icy rings. Their optical depth is low to moderate, never exceeding 0.1, making them difficult to observe even with powerful telescopes. These rings are ghosts, barely visible whispers of material orbiting a world at the edge of the solar system. But perhaps Neptune's greatest mystery orbits the planet rather than comprising it. Triton, Neptune's largest moon, is one of the strangest objects in the solar system. It's the only large moon that orbits its planet in a retrograde direction, revolving opposite to Neptune's rotation. This backward orbit proves Triton wasn't born alongside Neptune. It was captured, probably from the Kuiper Belt, where it once wandered as an independent dwarf planet. That capture event would have been catastrophic. Triton's arrival would have scattered or destroyed any moons that orbited Neptune previously. Gravitational interactions during capture would have left Triton in a highly elliptical orbit initially. Tidal forces would have circularized that orbit over millions of years, generating enormous heat in Triton's interior through tidal flexing. Even today, billions of years after capture, Triton displays remarkable geological activity despite surface temperatures of negative 235 degrees Celsius, making it one of the coldest objects ever measured in the solar system. Voyager 2 discovered active geysers on Triton during its 1989 flyby. These nitrogen geysers erupt through Triton's icy crust, creating dark plumes that rise 8 kilometers above the surface before being swept downwind by Triton's thin atmosphere. The energy source powering these geysers remains debated. Seasonal heating from the distant sun might create subsurface nitrogen reservoirs that explosively vent. Residual tidal heating from Triton's ongoing orbital evolution could provide heat, or radioactive decay in Triton's rocky core might generate enough warmth to drive these eruptions. Triton's fate is sealed. Tidal interactions cause its orbit to gradually decay. In approximately 3.6 billion years, Triton will pass within Neptune's Roche limit, the distance where tidal forces overcome the moon's self-gravity. At that point, Triton will either collide with Neptune's atmosphere in a spectacular impact or break apart, forming a new ring system potentially rivaling Saturn's magnificent rings. Future astronomers, if they exist, will witness Neptune adorned with brilliant rings composed of Triton's scattered remains. Our knowledge of Neptune comes almost entirely from a single spacecraft encounter lasting just hours. On August 25th, 1989, Voyager 2 made its closest approach to Neptune, culminating the spacecraft's grand tour of the outer solar system. The flyby was technically challenging.